Welcome to today's lesson. We are going to look at prime decomposition. With prime decomposition, previously we had looked at the prime numbers. Prime numbers, we simply said that prime numbers are numbers that have only two factors, that is 1 and itself. An example of prime number we were looking at is 2. Another example of prime number, we have 3. Another example of prime number is 5, 7, 11, 13, 17, and so on. So those are examples of prime numbers we have. So with prime decomposition, what we are simply doing is we are expressing a composite number. So we are expressing a composite number as a product of its prime numbers. Product of its prime factors. So we are expressing a composite number as a product of the prime factors. So its prime factors, when expressed as a product, then what we've simply done is prime decomposition. So expressing a composite number as a product of the prime factors. And as we are looking at the product of the prime factors, it brings us back to whatever we talked about on indices, that a number can be expressed in an index form. So when we are talking about an index form, we are simply talking about this number being written to the power of another number. So like for example, we are having 2 to the power of 4. This is the index form of the number 2 times 2 times 2 times 2, which is simply 16. So 16 to the power 4 is 2 to the power of 4. So with the prime decomposition, what we are simply doing is we are expressing this 16 as a product of its prime factors. Then we discover that the prime factors of 16 are 2 repeatedly 4 times. So when you multiply the 2 4 times, then we get the prime factors of 16. So 2 to the power of 4 has been decomposed. The 16 has been decomposed to 2 to the power of 4. So we just look at prime decomposition using the tree factor. So the first example we are looking at is 45. So we want to decompose 45 as a product of its prime factors. So we need to find out 45, what is its prime factors. And we discover that the first prime factor that can divide 45 is 5. 5 into 45. The first prime factor, the lowest, is 3. 3 into 45, we have 15. The next prime factor, we have 3. 3 into 15 is 5. Then 5 into 5, we have 1. So we discover that if we express 45 as a product of its prime factors, we have 3 times 3 times 5. 3 times 3 has been repeated, so we can write it in power form. So 3 times 3 is simply 3 squared times 5. So 45 decomposed into its prime factors will be 3 squared times 5. Another number we have is 600. So we want to decompose 600 as a product of its prime factors. So the first number is 600, then we have the two arrows. The lowest prime factor that can divide 600 is 2. 2 into 600, we have 300. Another prime number, we still have 2. 2 into 300 is 150. Still 2 into 150 is 75. The next prime number we have is 3. 3 into 75 is 25. Then the next prime number is 5. 5 into 5, we have 5. Then 5 into 5, that is 1. 5 into 25, 5. 5 into 5, 1. So the prime factors that are making up 600, we have 2 times 2 times 2 times 3 times 5 times 5. So if we express it in index form, 2 is repeated 3 times. So we have 2 to the power of 3. Multiply by 3 times 5 is repeated twice. So it is 5 to the power of 2. So if I decompose 600 into a product of its prime factors, we are having 2 to the power of 3 times 3 times 5 squared. Another number we can work with to get its prime factors is 72. So 72, the first prime number we have is prime factor is 2. 2 into 72, we have 36. The next prime number, we still have 2. 2 into 36, that is 18. We still have 2 into 18, that is 9. The next prime number is 3. 3 into 9, 3 times. Then we have 3 into 3, 1. So if we express 72 as a product of its prime numbers, we have 2 times 2 times 3. I mean 2 times 2 times 2 times 3 times 3. Meaning 2 is repeated 3 times. So 2 being repeated 3 times, you have 2 to the power of 3 multiplied by 3 to the power of 2. Let us find out the prime factors of 111. So with 111, we find that 2 is not divisible. The 111 is not divisible by 2. Let us find out if it is divisible by 3. 1 plus 1 plus 1 is 3. So it means that this number is divisible by 3. So our first prime number is 3. So 3 into 111. Into 11 we have 3. Into 21 we have 7. So 3 into 111 is 37. The next prime number we have is 37 into 37 once. So it means 111 expressed as a composite of its prime factors will be 3 times 37. 96, we express it as a composite of its prime factors. So we have 2 into 96 is 48. 2 into 48, we have 24. 2 into 24, that is 12. 2 into 12, we have 6. 2 into 6, that is 3. Then 3 into 3, we have 1. So when we express it as a product of its prime factors, we have 2 has been repeated 5 times, then 3 is appearing once. So we have 96 is the same as 2 times 2 times 2 times 2 times 2 times 3. So this means 96 is the same as 2 to the power of 5 multiplied by 3. So expressing 96 as a product or as decomposed product of its prime factors, we have 2 to the power of 5 times 3. Another number we can express as a product of its prime factor is 144. So the first prime factor we have is 2. 2 into 144, we have 72. 2 into 72, that is 36. 2 into 36, we have 18. 2 into 18, that is 9. Then 3 into 9, we have 3. And finally 3 into 3, we have 1. So we have 2 repeated 4 times. So 2 times 2 times 2 times 2. 3 is repeated twice, that is 3 times 3. So if I express 144 as a product of its prime factors, we have 2 to the power of 4 times 3 to the power of 2. So apart from using the tree factor, we can decide to use the division by prime numbers as an option of finding out the factors that are dividing or the factors that are making up a composite number. For instance, if I'm having 60 as a number, I need to find out which are the prime factors that are making up 60. So what does it mean? If I'm using tree factor, then it means we have the 2 arrows, so that 2 is our first smallest prime number that divides 60 into 30. Then the next one we have 2, 15. The next one we have 3 into 15, that is 5. Then we have 5 into 5, we have 1. But apart from using this tree factor, we can use division method so that we find out which are the numbers that are making up the prime factors of 60. This is what we mean, that instead of using this tree, I can decide to go ahead and use the division way, in which still the same is applying. We are having to divide from our lowest prime factor. The lowest prime factor we have is 2. So 2 into 60, 2 will divide 60 30 times. Then the next is still 2. 2 into 30, we have 15. Then we have 3. 3 into 15 will give us 5. And finally, we have 5. 5 into 5 is 1. So we have either this option or this. It still gives us the same result. So whichever you prefer, you can opt for whichever method that you prefer to use in finding out the prime factors that make up a given number. So in short, in these, the two solutions gives us the same answers. It means that the prime factors that make up 60, if we try to decompose into prime factors our 60, we are having 2 appearing twice, so it is 2 times 2. Then we have 3 times 5. So 2 times 2 is simply the same as 2 to the power of 2 multiplied by 3 times 5. So that is another alternative that we can use to get the prime numbers that are making up a given number. So keeping that in mind, keeping the idea of the prime numbers in mind and the process of the prime decomposition, I want us to solve this question. So we are having 144 and 96. We are told to express 144 and 96 in prime factor form. So it means I get the prime factors of 144 using whichever method. So if I'm having the prime factors of 144, the first prime factor we have is 2. 2 into 144 is 72. The next one is 2 into 72, we have 36. 2 into 36, we have 18. 2 into 18, that is 9. Then 3 into 9, we have 3. And finally, 3 into 3, we have 1. Then 96. 96, we are having the prime factors. The first prime factor is 2. 2 into 96 is 48. 2 into 48, 24. 2 into 24, 12. 2 into 12, that is 6. 2 into 6, we have 3. And 3 into 3, we have 1. So expressing them as prime factors, 144 will be given by 2 times 2 times 2 times 2 times 3 times 3, which gives us 2 to the power of 4 times 3 to the power of 2. 96, if we express it as a prime, expressing it in prime factor form, we are going to have 2 to the times 2 times 2 times 2 times 2, 5, then times 3. So when we express it in power form, we are having 2 appear in 5 times, so 2 to the power of 5, then multiplied by 3. Then after writing the numbers in power form, we are told to find the highest common factor. So how do we get the highest common factor? The highest common factor will be obtained by the factors that are appearing in both the numbers. So the factor that we can be able to get in 144 and at the same time in 96. So in this case, what are we getting here? We have 2 to the power of 5. We have 2 to the power of 4. So we find that 2 to the power of 4 is appearing here, 2 to the power of 4 is appearing here. So if this 2 to the power of 5 is just the same as 2 to the power of 4 times 2 to the power of 1, meaning this 2 to the power of 4 is here, we also have 2 to the power of 4 on the other side. So it means 2 to the power of 4 is the lowest factor that we are meeting here, that is common in both 144 and 96. We also find a number, and the other number that is, the other factor that is common, and we get that 3 is common here, 3 is common here. 3 squared is just the same as 3 times 3. So I can get 3 here, I can get 3 from this point. So it means the other number I have is 3. So the highest common factor from our calculation will be obtained by 2 to the power of 4 times 3. And 2 to the power of 4 is 16. 16 times 3 gives us 48. So we get that 2 to the power of 4 times 3 gives us 48. So the highest common factor in 144 and 96 is 48. We can confirm if 48 can divide 144 and at the same time divide 96. So we just want to confirm. So 144 divided by 48, highest common factor. So a factor we said is just that number that fully divides a number without a remainder. So we find out, is there any remainder if 48 divides 44 or not? So 48 into 144, and we get that 48 in 144 is 3. 3 times 8, that is 24, carry 2. 4 times 3, we have 12. 12 plus 2, we have 14. So we get that 144 is simply 48 divided by 144 divided by 48 is simply 3. Then if we have 96, 96 divided by 48 is 2. So the highest, we find that 48 can divide both 96 and 96 and 144. So what does it mean? That our highest common factor, the highest factor that can divide both 144 and 96 is 48. So we are given some prime factors and we are supposed to convert the prime factors that have been written into powers. So we have 2 times 3 times 3 times 2 times 2. So we write these prime factors using powers. So we try and collect, we have 2 at this end, we have 2 at the first point, so we can bring the 2's to one side such that we have 2 times 2 times 2 times 3 times 3. Then we simply said earlier on that when you are writing powers, you simply have a base, then the number is acting as the base, then count the number of times that number is repeated. The number of times the number is repeated gives us the power. So we find that here we have our base as 2. Then how many times has the 2 been repeated? We have 1, 2, 3. So the 2 has been repeated 3 times. So it means it is 2 to the power of 3 times the second power, the base we have is 3, and 3 has been repeated twice. So the power of 3 in this case will be 2. So writing these prime factors in power form, then we have 2 to the power of 3 times 3 to the power of 2. Next we have 5 times 3 times 3 times 3 times 5. So we discover that we have 3 has been repeated 3 times. So I have 3 times 3 times 3. Then we have 5. So 5 times 5. So my base here is 3 and it has been repeated 3 times. So it means 3 to the power of 3. Then the next base is 5. 5 has been repeated twice, so it means that I have 5 to the power of 2. Next we have 7 times 2 times 3 times 7 times 2. So my lowest factor that I have here is 2, and I discover that we have 2 repeated twice, so I have 2 times 2. The next one is 3. 3 is only appearing once. Then next I have 7 appearing twice, so 7 times 7. So after that, we write it in power form. The first base I have is 2. It is repeated twice, so it is 2 to the power of 2. The next number is 3. It is just appearing once. There is no need of writing to power 1 because a number written to power 1 is simply that number. Then multiplied by 7 is appearing twice. So 7 appearing twice gives me 7 to the power of 2. So 7 times 2 times 3 times 7 times 2 is simply 2 squared times 3 times 7 squared. 3 times 3 times 2 times 11 times 11 times 2 is another prime factors that we have. So our lowest prime factors, we have 2 appearing twice, so I have 2 times 2. 3 is appearing twice, so I have 3 times 3. 11 is also appearing twice, I have 11 times 11. So writing it in power form, 2 is appearing twice, that is 2 to the power of 2. 3 is appearing twice, we have 3 to the power of 2, and 11 is also appearing twice, so I have 11 to the power of 2. Another question. So the numbers we have, A is, we have 120, B we have 150, C we have 144, and D we have 180. Then the set of prime factors we have are the following. A, we have 2 times 3 times 5 to the power of 2. Then the next set, we have 2 to the power of 2 times 3 to the power of 2 times 5. The next set of prime numbers we have is 2 to the power of 4 times 3 to the power of 2. And finally, we have 2 times 3 times 2 times 5 times 2. So what we need to do is match the number on with the small letter with the correct prime factors which have capital letters. So we need to identify which prime factors are matching the number on this side. So what do? We first start by starting with the first one. I have 120. So 120, I need to find out which prime factors are making up 120. So finding out the prime factors making up 120, I'm having 120. Then the lowest prime factor is 2. 2 into 120, we have 60. 2 into 60, that is 30. 2 into 30, we have 15. 3 into 15, that is 5. 5 into 5, 1. So the prime factors, we have 2 to the power of 3 times 3 times 5. So I find out which prime factors on that side are matching what I have. 2 to the power of 3 times 3 times 5. So we get that this is 2. It is not to the power of 3. Kwa hivyo the A doesn't match. B, we have 2 to the power of 2. So 2 to the power of 2 is not the same as 2 to the power of 3, so they don't match. C, we have 2 to the power of 4. This is 2 to the power of 3, meaning they don't match in that case. D, we have 2 times 3 times 2 times 5 times 2. What does it mean? I need to find out the powers that are representing the numbers in this case. So I have 2 times 2 times 2. 2 is repeated 3 times. So 2 being repeating itself 3 times is the same as 2 to the power of 3. Then 3 is repeating once, so we have times 3. Then 5 is repeated once, we have times 5. So which number is matching the powers I have on this side? It automatically means that 120 will match 2 times 3 times 2 times 5 times 2. So I have the next number is 150. 150, we get the prime factors of 150. 2 into 150, that is 75. 3 into 75, we have 25. Then 5 into 25, that is 5. 5 into 5, we have 1. So if I express the number as a product of its prime factors, we have 2 times 3 times 5 squared. So I find out which number is matching what I have. 2 times 3 times 5 squared. So from this side, 2 times 3 times 5 squared is at that point. So 150 is the same as 2 times 3 times 5 squared. The next number is 144. So 144, getting the prime factors of 144, we have 2 into 144, that is 72. 2 into 72, we have 36. 2 into 36 is 18. 2 into 18, 9. Then 3 into 9 is 3, and 3 into 3, we have 1. So expressing 144 as a product of its prime factors, we are having 2 repeated 4 times, so that is 2 to the power of 4, then times 3 to the power of 2. So 144 on this side matches with 2 to the power of 4 times 3 to the power of 2. What does it mean? The remaining number is what will represent our 180. So I'm left with 2 squared times 3 squared times 5 as the prime factors that are representing 180. So we just write them down, showing the exact prime factors. So transferring my answers, we've talked about 120. The prime factors representing 120, we have 2 times 3 times 2 times 5 times 2. Another number we were having is 150. So a number representing prime factors that are representing 150, we have 150 is the same as 2 times 3 times 5 squared. Then another number is 144. So 144 will be represented by 2 to the power of 4 times 3 to the power of 2. Then finally 180 is represented by 2 to the power of 2 times 3 to the power of 2 times 5. So those are the prime numbers that are representing, or the prime factors representing the composite numbers in each case. Another question, we are asked to fill in the gaps in each of the following. Fill in the gaps to complete the following factor trees. We have 40. then we have that gap, and this is given as 8. Next we have that gap, and we are having 2. Then the other one, we are having a gap at this point, so that we have 2 and 2. So we need to fill in the gaps. So this is what should happen. This is 40, and there is a number, a digit. When I divide 40 by that digit, I'll get 8. So what does it mean? This number that I'm looking for, that if I take 40 divided by a certain number, let's say x, it should give me 8. So how do I get this value of 40? So this is 40 over x is equal to 8. So that means that if I multiply this side by x, multiply this side by x, 40 will be equal to 8x. So that means divide by 8, divide here by 8. Our value for x is 5. So this means that if I take 40 divided by 5 will give me 8. So I'm filling in the gap, and that gap should be having 8. Next, we have a number. If I divide that number, the number I divides 8 2 times. So which number can divide 8 2 times? The number is simply 4. So we have 4 into 8, we have 2. Then this 4, when we get the prime factors of 4, we have 2 and 2. 2 times 2 will give us 4. 4 times 2 will give us 8, and 5 times 8 will give us 40. So filling in the gap, that is what is expected of us. Another 3 factor we have to fill in. We have the number 30 as our starting number. The 2 arrows, we have 3 and a dash at that point. That is what we need to fill in. Then from there, we have another dash somewhere that we need to fill. That gives us 3. This is supposed to be 5. So we have 3 divided by 5. What do we get? When we divide 3 by 5, we are supposed to get 6. Then using the factors of 6, 6 is simply 3 times 2. So this box requires the number 2. So we get that we are filling in the gaps, and our gap will be filled in by the number 6 and 2. We have another number that is 100. Then the 100, we have the number 10 and that gap. Then from there, we have 2 gaps. These 2 gaps have 2 numbers that need to be filled in. Then next we have this gap has the number 2 times 2 and 5 as the numbers that are here. So how we are filling in the gap. So which numbers can divide 100 10 times, or 100 divided by 10, we are supposed to get the value as 10. So that 10 times 10 gives me 100. 2 times 5 will give me 10. So this means that in one way or another, this 3 factor is helping me fill in the gap on the other side. Which numbers can I multiply to get back 10? It is simply 2 times 5, which will give me the 10. So that is the factor trees, a way of finding out the factors that make up a composite number. So finally, just to remind ourselves what we've been going through, we've been looking at prime decomposition, and as we look at the prime decomposition, we need to know the difference between prime numbers. The knowledge of prime numbers and composite numbers is what is helping us in decomposing composite numbers. So we discover that we've said that prime numbers are simply those numbers that have only two factors, 1 and itself. Composite numbers are those numbers that have more than two factors. So when you get a number that has more than two factors, then it is a composite number. Then in decomposing these composite numbers into a product of its prime factors, you need to find out which prime numbers or which prime factors make up the number. So find out the prime factors that make up the composite number. Then after you've found the prime factors that make up the composite number, there are two ways in which you can get the prime factors that make up the composite number. The prime factors can be obtained using the factor tree method. So we have the factor tree method, or we can go ahead and use the division alternative. So we have division alternative and the factor tree method. Those are two ways in which we can get the prime factors making up the composite numbers. After you've gotten the prime factors making up the composite numbers, find out if there are any prime factors that are repeating themselves. If you get the prime numbers that are repeating themselves, then it is good or it is advisable to express those prime factors that are repeating themselves in index form. So you express them in index form so that the power that will be indicated on that number shows the number of times the number is repeating itself. So if the number is repeating itself 5 times, you write the number to the power of 5. If the number is repeating itself 10 times, then it means it is to the power of 10. If it is repeating 7 times, it means that it is to the power of 7. So the task you have after getting the prime factors that are making up the composite numbers, you find out which numbers are repeating themselves. Then you simply express them as a power form, but they are expressed as a product of these prime factors. So we get the product of the prime factors making up, keeping in mind that the prime factors that will be repeating themselves can be expressed in index form. So what does it mean? It leaves us with some questions that we need to think about. The question is, we have a list of numbers here, and we need to find out, are they composite or are they prime numbers? So let us just try and find out, are our numbers composite or are they prime numbers? And if they are composite numbers, are we in a position to express them as a product of their prime numbers? So the first number we have 15. We need to find out, is 15 a prime number or is it a composite number? So we need to find out which factors are making up 15. We said we have two ways. We can use the factor tree method or we can use the division method. So let us use the factor tree. 15, the lowest factor we have, 1 plus 5 is 6, so 6 is divisible by 3, so we have 3 into 15, that is 5. Then the next number we have is 5 into 5, 1. So 15 has these the factors that are making up 15 is 3 times 5 times 1. So 3 times 5 times 1, you discover that 15 has those numbers making it up. So meaning 15 is a composite number. So 15 being a composite number, we can express it as a product of its prime factors. And the prime factors that are making up 15 is 3 and 5. Keep in mind, we said that 1 is not a prime factor because it only has one factor. Prime factors have two factors, but 1 is not a prime factor. So in this case, I'm only having 3 and 5 as the prime factors. So expressing my composite 15 number as a product of its prime factors, 15 will be equal to 3 times 5. Another number we have is 13. We need to find out, is 13 a prime number or is it a composite number? So 13, using the factor tree method, we have 13. 13 into 13 is 1. So we find that 13 has only two factors, that is 13 and 1. Having the two factors, it means that 13 is a prime number. So being a prime number, it means that I have no other number that I can multiply it with, because I don't have any other prime factor. 13 is the only prime factor that is available here. 1 is not a prime factor, so I can't express it as a product. So it means that my 13 is a prime factor. Another number I have is 7. And we discover that 7 also does not have another number apart from 7 and 1. So 7 into 7 is 1. So 7 is also a prime number. Then we have 8. We need to find out if 8 is a prime number or not. So 8, the lowest prime number that can divide 8 is 2. 2 into 8, 4. Then 2 into 4, we have 2. And 2 into 2, we have 1. So we discover that 8 is not a prime number because I can express it as a composite, a product of its prime factors. So I have 8 is simply 2 times 2 times 2. So the prime factors making up 8 is simply 2 to the power of 3. And you are saying that 8 is a composite number. So as I conclude the lesson, I want to leave you with a question to think about. This is what I need you to find out. Using the internet, find out with what is the largest non-prime number. So find out the largest non-prime number. So we have our Google to give us the answers to whatever we need to find out. So an assignment that is left for us as we look at the prime numbers and their decomposition, we are trying to find out which one is the largest non-prime number. So can we find out from the internet and try and get the required answers? What is the internet saying about the prime numbers, and what is that number that is being identified as the largest non-prime number? Thank you.